Integer division, dividend, divisor, quotient, remainder. We know that 14 can be made by taking 7 and multiplying it by 2. 35 can be made by taking 7 and multiplying it by 5. 56 can be made by taking 7 and multiplying it by 8. We say that 14, 35, and 56 are divisible by 7. And indeed, any integer that can be made by multiplying 7 by some integer is divisible by 7. However, some integers can't be made by multiplying 7 by some integer. So, for example, 17 can be made by multiplying 7 by 2 and then adding 3. Or minus 31 can be made by multiplying 7 by minus 5 and adding 4. 55 can be made by multiplying 7 by 7 and adding 6. In these cases, we say that the integers are not divisible by 7. To make them, we multiply 7 by some integer, and then we have to add an integer which is between 1 and 6 inclusive. And in fact, every single integer, whether it be positive, negative, or 0, is either divisible by 7, which means it can be made by multiplying 7 by some integer, or it can be made by multiplying 7 by some integer and then adding an integer between 1 and 6 inclusive. Now, usually we combine these two possibilities. So if we look at the numbers that are divisible by 7, we see that 14 is 2 times 7 plus 0. 49 is 7 times 7 plus 0. Minus 21 is minus 3 times 7 plus 0, and so on. For the numbers that are not divisible by 7, say 25, that is 3 times 7 plus 4. In both cases, the way we make those integers conform to this formula. A, the integer we wish to make, is q times 7 plus r, where q is some integer and where r is a non-negative integer that is strictly less than 7, i.e. r can be 0, 1, 2, 3, 4, 5, or 6, but not 7. And so we're saying that every integer in the set Z, the positive, negative, and 0 integers, can be made by multiplying 7 by some integer in Z and adding an integer between 0 and 6. In the case where the integer that we add is 0, then we are creating an integer that is divisible by 7. If the integer we add is not 0, we're creating an integer that is not divisible by 7. And it's worth pointing out that since we can think of integer multiplication as being repeated addition, i.e. that 3 times 7 is simply shorthand for 7 plus 7 plus 7, then we could think that we are creating integers by repeated addition of 7. So to state this fact a little more formally, we can say that for all a in Z, which means all integers positive, negative, or 0, we can find some q in Z, so q itself might be positive, negative, or 0, such that a equals q times 7 plus r with the restriction on r that we stated before. R is non-negative and strictly less than 7, and R must be an integer. So R can take one of the values 0, 1, 2, 3, 4, 5, or 6, and nothing else. Now, why do we have this restriction on R? Could we not take an R bigger than 6? Well, the answer to that is yes. So, for example, we can create 57 from 7 by multiplying it by 6 and adding 15, which is greater than 6. We can note that we can take 15 and break that down into 14 plus 1. And 14 is 2 times 7. So we can create 14 from 7 by multiplying it by 2. We can then combine 6 times 7 plus 2 times 7 into 8 times 7, and then we have to add the 1 that was left over when we decomposed 15. So the restriction on R is ensuring that we are forced to make Q as large as possible. If we don't make Q as large as possible, we start off with a remainder that itself can be decomposed into 7 times some other integer. However, once we have made Q as large as possible, we're left with only one choice for R. It is a unique value. And it is a unique value that lies between 0 and 6 inclusive. On the other hand, if we don't make Q as large as possible, then R will not be unique. We could choose various values. So if we choose Q to be 5, which is smaller than the maximum possible 8, then we can make 57 by 5 times 7 plus 22, which is different to the 15 which we used originally. We don't get a unique R if Q is not as large as possible. Now, we can also consider this from the point of view of integer division. Whereas integer multiplication is equivalent to repeated addition, integer division is equivalent to repeated subtraction. So let's consider the problem 31 divided by 7. We want to produce an answer that only involves integers, and to do so, we use the idea of repeated subtraction of 7 from 31 until it's no longer possible to subtract any more. Here we have a visual representation of this process. We start with 31 and subtract 7 to leave 24. From 24, we subtract 7 to leave 17. From 17, we subtract 7 to leave 10. We subtract 7 from 10 to leave 3. And now we can no longer subtract 7 without producing a negative integer, a negative remainder, as we call it. We could subtract 7 from 31 4 times before we were about to produce a negative number, and we call 4 the quotient. The 3 that was left over at the end of the process of subtraction is called the remainder. 31, the number we started with, is called the dividend. 7, the number we are dividing by, is called the divisor. And we more usually write down that process symbolically by saying 31 divided by 7 is 4, remainder 3. And this division representation of the problem is equivalent to the representation we used before. 31 equals 4 times 7 plus 3. These two statements say exactly the same thing. In our earlier notation, 4 is Q and 3 is R. Now, I mentioned earlier that we wanted to make Q as large as possible to ensure that R was a unique number between 0 and 6. And it's exactly this process of repeated subtraction until we can't continue that ensures that the quotient, the Q, is as large as possible. Now, we've been using 7 to construct integers, but in fact, any integer at all, with the exception of 0, will do the job just as well. So we can construct minus 17 from minus 4 using the formula 5 times minus 4 plus 3, which we can equivalently write as minus 17 divided by minus 4 is 5 remainder 3. And please note again that 3, the remainder, is non-negative. In fact, the remainder is always non-negative, even when we are dividing by a negative number. And we can see how this works using the illustration here, where we represent the signed numbers as vectors, as arrows. So minus 4 is an arrow pointing to the left of the number line. So we want to construct minus 17 from minus 4, and we have to do so by repeated addition. This is what this formula is telling us, and we need to end up with a positive remainder. So to produce minus 17, we start off with minus 4, add minus 4 to take us to minus 8, minus 4 to minus 12, minus 4 to minus 16, which isn't quite far enough, then minus 4 to minus 20, which is too far, so we have to come back by plus 3 to produce the minus 17 arrow, which points to the left. And note in this case that the remainder 3 is less than the length of the minus 4 vector, the minus 4 arrow, i.e. it's less than the modulus of minus 4, which is 4. And the modulus function, mod x, always spits out a positive number. If x is greater than or equal to 0, it spits out x. If x is a negative number, less than 0, it spits out minus x, which is positive, of course, if x is negative. And of course, this approach to constructing integers has nothing at all to do with 7 or minus 4. It works with any divisor at all, with the exception of 0. And so we have the following fact. Let a and b be integers in z, with b not equal to 0. So we are going to use b as our divisor, and a will be our dividend, the number we want to construct. Then we can construct a as q times b plus r, where q and r are appropriate integers in z, with the restriction that r be non-negative and strictly less than the modulus of b, than the size of b, which ensures that r is non-negative. And we call a the dividend, the number we're trying to construct, b the divisor, the number from which we are constructing it, q is the quotient, and r is the remainder. And as long as we choose an r that satisfies this condition, then q and r are unique. There's only one possible pair of values from which we can construct a from b using this formula. And to illustrate that, let's look at the construction of 3285 from divisor 19. So if we want r to be less than q, we find that we have to choose r is 17 and q is 172. If we choose q to be 172, we will find that we can use no other value than 17 to create 3285. On the other hand, we can choose q to be 171, but then the remainder r is not less than 19, so it does not satisfy this condition. And as mentioned before, if we say a equals q times b plus r, that's equivalent to saying that a divided by b equals q remainder r. Now, this fact is often called the Euclidean Division Algorithm or the Euclidean Division Lemma. And it's perhaps worth saying that Euclidean Division Algorithm isn't a great name for this fact because the fact isn't an algorithm in the classical sense. Also, Euclidean division is sometimes applied to a totally different process, so these names are somewhat ambiguous. However, we're stuck with them for historical reasons. Now, we are not allowing b to be 0, i.e. we're not allowed to use 0 as a divisor. Why is that? We can look at it from 2 points of view. Firstly, from the point of view of multiplication, and secondly, from the point of view of division. So, from the point of view of multiplication, if b equals 0, then from this restriction, r must be greater than or equal to 0 and less than 0, i.e. we would have to have r non-negative and negative simultaneously. So, r cannot be defined if b equals 0. That's the first problem. There's another one. If b equals 0, then from this formula, a equals q times 0 plus r. Q times 0 is 0, so we end up with a being 0 plus r, which is r. In other words, if we choose b equal to 0, then a will only ever be equal to r, and r, of course, can't even be defined, so this is hopeless. We can't construct any integer a at all if b equals 0. From the point of view of division, things aren't any better. If we divide a by b, we want to find the quotient q by repeated subtraction, and in this case, we would be performing repeated subtraction of 0 from a. What happens if we try that? Well, a minus 0 equals a, that's fine. And then we better do that again, it's repeated subtraction. A minus 0 equals a, and then again, a minus 0 equals a. We're not really getting anywhere, are we? Repeated subtraction of 0 gets us nowhere. It doesn't change the value of a. It doesn't reduce it. So we cannot find a quotient q if b equals 0. And so neither the multiplication point of view nor the division point of view make any sense at all if we allow b to be 0.